All right, Unit 3, Test Study Guide. Topic number 1 is an introduction to our 3 parent functions that we focused on during this chapter: linear, absolute value, and quadratic. So just in this one, we're writing down the parent function, graphing the parent function, just so you get an idea of what we're going to be starting with before we do any transformations. So the linear parent function is just f of x equals x. It's a very simple linear function. It starts at the origin and then it goes with a slope of 1 throughout the entire graph. So slope of 1, we'll just take it this way, or you could reverse by going down and to the left as well. So this is our linear parent function. Oops. So we use that to, change the slope, change the y-intercept, make different transformations like that. Absolute value, the parent function without any transformations, is just the absolute value of x. And this one starts at the origin as well. The right-hand side looks exactly like a linear function, but then the left-hand side, where this one goes down negative, this one reverses and goes back up positive. So that's what the absolute value graph looks like. Anything that was negative in this graph reverses and becomes positive in this graph. And our third type that we use in this chapter is the quadratic, and that parent function is x squared. So we have, again, starting at the origin, and then this one, when we square the 1, it goes up to 1, and it has symmetry. When we square the 2, it goes up to 4 and has symmetry. So this one is similar in a way to the absolute value, except it's got this curved and more steep shape as it moves out from the origin. So those are 3 parent functions that we transform throughout the entire chapter, and we'll be practicing now. Topic number 2, we can transform these functions. So this is just kind of writing down in general what the transformation rules do. And then as we move throughout this review, we will be actually transforming them. So first type, when you have the function, so it could be the x, the absolute value of x, or the x squared, this means that the plus h is on the inside with the x, so like inside the absolute value or inside the squared. That means you are going left h, whatever h units are. So if you had like the absolute value of x plus 4, for instance, you'd be going 4 units to the left. If it's on the inside of the function, but it's subtraction, that moves to the right h units. 3 units, 5 units, whatever it is. Oops, sorry, I said 4 in the last one. This should be an h. Sorry about that. This one, if the plus k is separate from the function, like it's outside the absolute value or outside the square, that is an up or down movement, and this one does not do the opposite. So when it's plus, it actually is up. When it is minus, it actually is down. So remember, h and k is a numerical value, so that's how many units you're moving in each direction. If there is something multiplied by the function and that value is bigger than 1, that is going to be a vertical stretch. And so what this means basically is if your graph used to move up 1 unit, it will now move up whatever a units is. So up 2 units, up 3 units. If this value is a fraction, or if it's something smaller than 1, this will be a vertical compression, which basically makes the graph look shorter and wider than it did before. And finally, if there's a negative in front of the parent function, this is going to be a reflection across the x-axis, which essentially means you're flipping it upside down. Okay, so we've got that summed up. Let's move on to topic number 3, which is about absolute value functions. So you guys have a vertex form for absolute value, which is really similar to the vertex form for a quadratic. So the a goes out front, and then in the absolute value you have x minus h, and then outside the absolute value there's a plus k. So absolute value is almost always given to you in vertex form. There really isn't another form. So you use that to figure out where your vertex is, and then you can graph based on that. So this one, when you look, the vertex, remember, is the opposite of whatever is inside the absolute value. So that would be a positive 2 for x, and then the exact value that you see on the end here for y. So that is your vertex. So it is 2, -7. So we're going to start with that. So 2 for x, and then 1, 2, 3, 4, 5, 6, 7 for y. Notice with a, there's nothing out front here that would shift at all. So you really do just go up 1 over 1. Remember, to the right, you use a slope of 1. And then we talked about in the notes how to the left you use the opposite of whatever a is. So to the left, we use a slope of -1, which would take us up and to the left. Okay, so you've got this shape that we just kind of continue on going this way. So our absolute value graph will look like that. Domain for every single absolute value graph is always all reals. And the range depends on what the y value for the vertex is. So the lowest possible point here is our -7, and it goes up from there. So we include all y values that are above or including the -7, which is our lowest point. All right, so that was our first one. We've got another one on the next page. All right, so that one, you can start by finding the vertex. So I mentioned that the vertex was the opposite of what you had on the inside for the x-coordinate. So if there's nothing on the inside, then the x-coordinate would be a 0, and then you use the exact value that you have right here. So 0, 4, we can go right there, start by plotting the vertex, and then to plot the rest of it, when you go off to the right, you use this number as the slope. So down 2 to the right 1, down 2 and to the right 1. And when you go off to the left, use the opposite of this number. So we use a slope of +2 off to the left. So this goes down and to the left like that. All right, so that is what our absolute value graph should look like. The domain, like I mentioned with the previous problem, always all reals for every absolute value graph as long as it's not part of a piecewise function, which will be coming up later. The range depends on the y value of the vertex. Here it hits a maximum value of 4 and then it goes down. So you would say your range is all of the y values that are less than or equal to 4, since it's an upside down absolute value graph. All right, so now we're going to give you some transformations and then have you write what the function would look like. So we are going to transform the parent function, write down a new equation, and then identify what the vertex would be. So our graph is shifted 5 units to the left and reflected about the x-axis. Okay, so f of x equals, if there's a reflection about the x-axis, there's a negative sign in front of the absolute value. And then shifted 5 units to the left, remember, left would be x plus, and that's where the 5 goes right there. So that is the initial, and then the vertex, you want to write that down too. So the vertex, remember, for the x-coordinate, you use the opposite of what's inside the absolute value, and for the y-coordinate, you use what's on the outside here, and with nothing on the outside, it would be 0. Number 4, we'll do something very similar. So you start with f of x equals, so it is vertically compressed by a factor of 1/3. So you'd have a 1/3 in front of the absolute value. Shifted 1 unit up and 2 units right. So 2 units right would be x minus, and then that's where the 2 goes. And 1 unit up, there would be a +1 after or outside the absolute values like that. And the vertex for this one, the x-coordinate is the opposite of what's inside with the x. That would be +2. The y-coordinate is exactly what you see there. So that would be a +1. All right, last piece that we have with absolute values is graphing inequalities. So with this, you graph it basically the same way as you did with the other graphs, except you may have a dashed line and then there's going to be some shading involved. All right, so the graph itself, let's start with our vertex. So the x-coordinate is a -6 and the y-coordinate is a -4. So we'll do that. 1, 2, 3, 4, 5, 6, and then down to -4. So that's the vertex. And then the number right here is just a 1. So we go up 1 to the right 1, up 1 to the right 1 a couple times, and then you repeat that same pattern in reverse on the other side. All right, so that's what the shape is going to look like. Next, look at the less than. So since it's just a less than, it doesn't have the or equal to, you're going to have a dotted line like that. And then it's less than, which means you shade below. Okay, so greater than you'd shade above, less than you shade below. So your graph would look like that. Very similar one for number 6. We write down the vertex. The x-coordinate is the opposite of the number on the inside, and then the exact number that's by itself on the outside. So if there is no number, we write that down as a 0. The vertex is at -3, 0, which would be right there on the x-axis. The number here kind of acts like a slope. So -2 means I go down 2 to the right 1, down 2 to the right 1, and I can reverse that off to the left. Okay, so that's my shape. My inequality is a greater than or equal to. So the or equal to means I use a solid line, and the greater than means I would shade up above. All right, so that is all of my absolute value stuff. Topic number 4 is quadratic functions. So we have 2 different forms. The standard form of a quadratic function looks like this. We have ax squared plus bx plus c, whereas the vertex form is one that's very similar to the vertex form for absolute value. We still have the a on the outside, and then this, instead of being inside an absolute value, is just inside a quadratic. But the rest of it is the same as the vertex form for absolute value. So this one, the vertex and the axis of symmetry, and then graph the function. So to find the axis of symmetry, we have this formula. We have negative b over 2a. So the opposite of the middle term, so negative 2 would be a positive 2. Over 2a would be 2 times 1. So 2 divided by 2 turns out to be 1. So that is the axis of symmetry. And then you immediately know from whatever the axis of symmetry is that that's going to be the x coordinate for your vertex. All right, that's true every single time. So we take that value and you plug it into the original function. So the y value, you find f at 1, and we can plug 1 into the equation. All right, so we took this equation right up here, and you're just replacing the x coordinates with 1 because that's the value that you got from the vertex formula. So we have 1 squared minus 2 times 1 minus 7, and that comes out to be a negative 8. So negative 8 would be the x coordinate, I'm sorry, the y coordinate for your vertex. So starting with the vertex, we have 1, and then down here at negative 8s. The rest of it, we make that table, remember? So I'm going to sneak in a table horizontally right here because we don't really have any room to make it vertical like we normally do. So x and f of x. So remember, whatever value your vertex is goes right in the middle, and then you go down a few from there. So we would go down negative 2, negative 1, 0. You'd have your vertex right in the middle, and then we'd go up 2, 3, 4. All right, so remember, these graphs have symmetry, so you can plug things into your calculator. We know that this comes out to be a negative 8, and then you can plug the values in off to the left and mirror them to the right, or vice versa. So let's go off to the left. So say I plug in 0 into this graph, so 0 squared minus 2 times 0 minus 7. That gives us a negative 7, which I can mirror on the right. Then I can plug in the negative 1. So that should be a 2. And I get a negative 4, which again, I mirror off to the right, and one more time with the negative 2. Okay, and that comes out to be 1, which I can mirror off to the right. Okay, so we've got those values. So off to the right, we go up to negative 7 and then mirror it. And then off to the right again, we go up to negative 4 and mirror it. And then one more time, we go up to 1 and mirror it. Okay, so those are your values for the parabola. Just connect the dots in our nice smooth curve. And then we can write down domain and range. So just like absolute value, the domain for every single one of these, as long as it's just a single function and not part of a piecewise function, it's going to be all reals because you can plug in any x value that you want. And then the range depends on where the vertex is, just like with absolute value. So our very lowest point here is a negative 8, and it just goes up from there because it's a minimum point. So my y values cover anything that's above that minimum value. So my range would look like that. All right, so we've got plenty more of these. Okay, so we have the vertex that we can find, the axis of symmetry. You're just going to be repeating that same process for all of these functions. So our formula, x equals negative b, which we don't have one, so it's 0, over 2a, so 2 times negative 3. So 0 divided by something turns out to be 0. So my axis of symmetry is 0. And then I will use that to set up a table, which I can actually squeeze in this time. So remember, in your table, the axis of symmetry goes in the middle. Okay, so we're going to plug in each of those different values, plug in 3 of them, and then mirror them. So negative 3 times x squared plus 5. So this first value is a negative 22, which would then mirror right here. Negative 2. I get a negative 7, which I mirror right here. And then negative 1. I get 2, which I mirror right here. And finally the 0. Okay, and that is 5. So we've got those values. The ones on the end, I'm obviously not going to be able to plot because they're too far outside the range of our graph, but we will still be able to plot the middle ones. So we have negative 3, negative 22, we can't plot, but negative 2, negative 7 is right there, negative 1, 2, 0, 5, and then mirror our points back down the other side. So that is what our parabola looks like, very narrow like that. Okay, so the vertex, when I plugged in 0, I got 5. You can see that on the table. The domain for every standalone quadratic is all reals, and then the range depends on my vertex. This time the vertex is a high point, so my y values are anything less than or equal to that high point. All right. These ones are given to us in vertex form now, so that's a little bit different. So 9, 10, and 11 are all given to us in vertex form. So the x of symmetry is just the opposite of this value that I have right here. So it would be a negative 3. For the vertex, I use the opposite of this value for the x and then this exact value for the y. So now I can make my table, plug the vertex in. Okay, so negative 3 is my middle value. Okay, and I know that this gives me 2, so let's plug those other 3 values into the calculator. Okay, so x plus 3 squared plus 2. So that value gives me 11, which will be off the graph, but that's okay. Same thing with the negative 5, x plus 3 squared plus 2. That gives me a 6. And one more value with the negative 4. That gives me 3. Okay, so I take these values and plot them. Like I said, I can't plot the first and last because it doesn't fit, but I can go to 1, 2, 3, 4, 5, and then down to negative 6. Oops, sorry, positive 6. So that should be going up here. Sorry about that. Negative 4 is at 3. Negative 3 is at 2, and then that's the vertex, so it mirrors back in the other direction. Okay, so our graph would look something like that. Back to domain and range. Remember, domain for every parabola is all reals. Range depends on where the vertex is. So this, the y value of the vertex is 2, and it just goes up from there. So my y values are those that are above the minimum value at 2. All right, 2 more of these in vertex form. So this one, our axis of symmetry, still the opposite of this. So x equals a positive 4 is my axis of symmetry. My vertex uses that value for the x and then whatever value is here for the y. So for that one, it would be a 0. And let's set up our table. Okay, so the positive 4 goes in the middle. And I know that's 0. So now let's plug the other 3 values into our calculator. So I can start with the 1. That gives me negative 9, which will be just slightly off our graph, so I can squeeze it in. And then the 2, which gives me negative 4. And finally the 3. Okay, so I can plot those values. So 1 is down at negative 9, so I can just go past a little bit. These ones are 8 in all directions. 2 is down at negative 4. 3 is at negative 1. 4 is at 0. And then you've got this symmetry. Okay, finish the rest of this table over here. Domain is all reals for every freestanding parabola. And the y values depend on where the vertex is. So the highest y value is 0, that's the maximum, and then my values just go down from there, so anything less than or equal to 0. All right, one more in vertex form like this. Axis of symmetry, you have an x minus 5, so your axis of symmetry is a positive 5. For the vertex, I use the opposite of this value for x and this exact value for y. And one last time, let's make a table. Okay, so the x-coordinate of 5 goes right in the middle, and then we go down 3 values and up 3 values. We know that this y value is a -6, and let's plug in the rest. All right, I'm going to use 0.5 instead of 1/2. So x minus 5 squared minus 6. First value is -1.5. And now the 3, so 0.5 times 3 minus 5 squared minus 6 is -4. And one more, 0.5 times 4 minus 5 squared minus 6. Okay, that is -5.5. Okay, so I'll plot these values, connect the dots, and I'll have my last parabola. So 2 is at -1.5, which you just estimate. 3 is at -4. 4 is at -5.5. And that's at -6. Okay, so then mirror these values back here, and then go ahead and connect the dots. Okay, so last domain and range for right now. Domain, still all reals. Every freestanding quadratic has a domain of all reals. And the vertex is what tells us the range. So all y values. The y-coordinate of the vertex is -6, and it's a minimum, so we go up from that point. All right, last things on these pages. The parent function, we're going to do some transformations, and we want to write what that new parent function would be, and we're going to write it in vertex form, and then identify the vertex. So we start with f of x equals for each of these. It's vertically stretched by a factor of 4, so that means there's going to be a 4 in front of the parentheses, and shifted 7 units to the right. So a right shift would be on the inside with the x, and it would be subtraction, and that's where the 7 goes, and then we finish off the parent function. So it doesn't say anything about up and downs, there wouldn't be an extra value there. Writing down the vertex, the x-coordinate is the opposite of the number right here, and then the exact number right here. Okay, one more of these. We start with f of x equals. It is reflected across the x-axis, so it starts with a negative. Vertically compressed by a factor of 1/2, then the parentheses. Then shifted 4 units left, so left goes inside the parentheses, and left is a plus rather than minus. And finish off the parent function, 6 units down would be -6 after the parent function. All right, so last piece is we want to identify the vertex. X is the opposite of the number in parentheses, and then the exact number here for y. All right, let's take a look at our next section, which is more quadratics. These ones are going to be inequalities. All right, so same rules apply as what we had with the absolute values. For these ones, you do the graph the exact same way that you did before. You just have maybe a dashed line and then some shading. All right, so these ones, you're going to start with your vertex. So x equals -6 over 2 times -1. So +6 divided by -2, which is -3. And then we can use that to set up a little table. All right, so I'm going to write small so I can sneak these values in. All right, so if I go down 3, I'd be -4, -5, -6. And there's my vertex, and then up 3. All right, sorry, we're sneaking that in. All right, so let's plug in the first 4 values and then talk about our symmetry. So -x². So notice the negative does go on the outside, and then the plugged in value goes in parentheses. Okay, and then -6 times -6 minus 1. So first value will be a -1, which gets mirrored. Second value is a -5, so -5 squared minus 6 times -5 minus 1. That is a 4, which is mirrored. Second to last one, -4 squared minus 6 times -4 minus 1. That is 7, and it's mirrored. And then let's finish off our last value, which is the vertex. -3 squared minus 6 times negative 3 minus 1. And that is a value of 8. All right, so plot those, and then we'll talk about what the inequality does. So negative 6, negative 1, negative 5, 4, negative 4, 7, negative 3 8, and then the symmetry. Okay, so before you connect the dots, make sure you're looking at the sign. The sign is a greater than or equal to. So the or equal to means it is a solid line, and the greater than means you shade above the parabola. So that would be everything up here. All right, let's do one more of those. This one's in vertex form already. So my vertex, I know for the x coordinate, I use a negative 4 from this value, and then a negative 4 for y for that value. All right, so let's set up our table. So the negative 4 is in the middle. So I go down to negative 7, negative 6, negative 5, and then there's my vertex, and then go up a few values. So that value I know from my vertex form, and then let's plug in the rest of them. Okay, so 2, then we plug in a negative 7 plus 4 squared minus 4. So that's my first value is 14, definitely going to be off the table. Next value, the negative 6, 2, negative 6 plus 4 squared minus 4. That's a 4, so that'll take us back onto the grid. And the last one is the negative 5, 2, negative 5 plus 4 squared minus 4. And that gives us a negative 2. Okay, so I can plot these values. I don't have to do the negative 7, 14, because that'll be way off the grid. But I can do negative 6, 4, and then negative 5, negative 2, negative 4, negative 4, and then there goes the symmetry. Okay, look at the symbol. The symbol is a less than, not a less than or equal to, which means I start this off with a dashed line. And then the less than means I shade below the parabola. Okay, next topic for quadratics is converting everything into vertex form. All right, so vertex form, I just want to write it here so that we have it in front of us. We kind of know the end goal. So it looks like that. All right, so each one of those, we are trying to get it into that form. So I want to go through our step-by-step process that we have. So step 1 of converting into vertex form is we want to group together, the ax squared plus the bx. So you kind of make a little group out of these. It's almost like you're ignoring that plus 64 for right now. If a isn't 1, factor out whatever a is, but we're safe here. So we move on to step 3, which is to complete the square. So you complete the square by taking this number in the middle, cut it in half, and then take what you get and square it. All right, so that gives us 64. So this, we're actually in this kind of weird position because the 64 is already the right value, and that's pretty rare that that happens. So we're still going to go through and do the process the way it's supposed to be done. So we are going to take this. This is the new value of c. We are going to add that into our little special group that we have here. That makes the perfect square trinomial. And then you want to subtract a times c to the end of the equation. So a is 1 times 64. You're going to subtract 64 from the end of the equation. Okay, last step, factor the trinomial and then simplify the end of the equation. So if I factor the trinomial, multiplying to 64, adding to negative 16 would be negative 8 and negative 8. So I write it in this squared form, and then that just ends up being 0. So you don't have to write the plus 0 for an equation like that. State the vertex. The vertex is the opposite of this number, so positive 8, and then the number on the end, which if there's nothing written, would be 0. Okay, we have 3 more of these, so hopefully you'll be good at this process by the time we're done. So step 1, group ax squared plus bx. Okay, so literally grouping it just means separating it out just like that, making it different from the negative 8. Step 2, if a isn't 1, factor out a, but a is 1, so we move on to step 3. Step 3, complete the square by taking half of b, so we take that number in the middle, cut it in half, and then square it, so we get 1. So this is the new c, So we add this to our group right here. So that C gets added to our little group in parentheses, and now this is the perfect square trinomial. Okay, so we still have this minus 8. Our next step is to subtract A times C from the end of the equation. So A times C is just 1 times 1. So we subtract a 1 from the end of our equation. And step 5, factor the trinomial and simplify the end of the equation. So the numbers that multiply to 1 and add to 2 would be 1 and 1. So x plus 1, x plus 1. I just write it squared and simplify the end of the equation. So that is our equation. Our vertex is the opposite of this number for x and then this number for y. So the opposite of x would be a -1, and then that value on the end would be the y coordinate. All right, number 18. So this one, you see we finally have an A, and we do here as well. So step 1 is group the ax squared plus bx. Step 2, we finally get to use, if A isn't 1, factor it outside. So A is a -1. So we factor that -1 outside. So this is now a positive x squared. This is now a -10x. Okay, so we did step 2. Step 3, complete the square by taking half of b and squaring it. Sorry, that was just supposed to be an equal sign. Add this to my group in parentheses. So that 25 that I just found, I'm going to add it right there. And then step 4, subtract A times C from the end of the equation. So we're going to subtract, and then A times C is -25. So I'm going to subtract a -25. And step 5, factor the trinomial. So this multiplying to 25, adding to -10 would be -5 and -5. So I can write that factor squared. And then simplifying this, changing it to plus a positive, I end up with a +2. All right, so that's my equation and my vertex. The x coordinate is the opposite here, which is +5, and the y coordinate is this number here, which is 2. All right, one more of these to get into vertex form. So same exact step-by-step process here. So first thing we want to do, step 1, is group the ax squared plus bx. Step 2, factor out a from my set of parentheses. So I'm going to factor out a -2. So this is now just an x squared. When I factor -2 out here, I'm left with -6x, like that. Step 3, complete the square by taking half of b and squaring it. This is the new c, so we've got the new c. Add this to the x squared plus bx in parentheses. So add the 9 right there. Step 4, subtract a times c from the end of the equation. So a times c is a -18, so we're going to subtract a -18 from my equation, like that. Okay, and then clean it up. So f of x equals, my next step is to factor this trinomial down. So we're looking for factors that multiply to 9 and add to -6. That would be -3 and -3, so I can write it squared. And this, when I combine them up, gives me a -1. So final equation, and our last vertex that we need to write down. The x is the opposite here, so that would be a +3, and then this value for y. All right, moving on to our next topic, piecewise functions. So you guys learned about piecewise functions first, but then you eventually started using them with absolute value and quadratic. So it's put in the back here so that we can just put all the piecewise stuff in one place. Okay, so graphing the function, remember it's basically the exact same way that you graph the normal lines, except we're going to do it in pencil so that we can adjust the domain once we have them graphed like this. So we're going to start with the first one, 2x plus 7. So we are going to go up to a y coordinate of 7, then use a slope of 2. So I can't go up and over, so I'll go down and left. So there's my slope of 2. I'll use just a few times here to get the shape of my graph. And then connect the dots. So my graph will look something like this. Remember, we're just doing a sketch in pencil right now, and then we'll adjust the domain. This one here is in y equals mx plus b as well, so that's just a line. This one starts at a y-intercept of 0, and then we use a slope of -1/4. So we go down 1 and to the right 4, down 1 to the right 4, and I can go the opposite in this direction. So up 1 and to the left. So that is my second line. Okay, so once I have that, now I take a look at the domain. Okay, so my domain splits at -4. All right, oops, this is really crooked. My domain splits at -4, so I go 1, 2, 3, 4, and this is where the actual split happens, is at that value. So I only use this graph, which is this one right here, up until -4, but not including -4. So it's this whole part right here, and then I'm going to have an open circle where the x-coordinate would be -4. So now I can connect the dots here. So open circle on the -4, and then this graph just going off to the left. Once I finalize the other piece, then I'll erase what I don't need. And then this piece we use starting at -4 and then going off to the right. So starting at -4, here we go. That's a closed circle because it has the or equal to, and then we use this graph off to the right. All right, so we have those two pieces in place, so really all that's left to do is get rid of the rest of it. And then you just have what's left over as your piecewise function. Okay, so you have those two pieces. The domain, you look at the x's, range, you look at the y's. So domain kind of scan from left to right. This one goes off to the left, this one goes off to the right. There is no missing x values in here because this one picks up right where the last one leaves off. So my domain would be all reals because every x value gets covered. The range, it goes down forever. There's a little bit of a gap here, but it's covered by these values. And then this is the very highest y value. So there are no y values above a +1. So that is our maximum value. So we say we'll hit anything below or including 1. Okay, so that would be the range for our first piecewise function. We've got 3 more on the next page, which is covering all the different types of graphs that we did. So number 21, we have an absolute value and we have a linear. So the absolute value, you graph the exact same way as we would have done on our previous couple pages. So you start with, for the absolute value, start with the vertex. So the vertex is a -2 for x, and then since there's nothing on the end, a 0 for y. So let's start plotting that. Remember, do it in pencil so we can erase what we don't need. So -2 zeros right there. The slope right here is a -1, so we use the slope of -1 off to the right, like this, and then we mirror that slope off to the left, like this. Okay, so connect the dots, and you can see, so we might as well actually stop that graph once we get to the 1. So like when you're starting to sketch, you can note where the domain is going to be and make the graph stop before you even sketch something that you're just going to have to erase anyway. So it goes up to an x value of 1, which ends right here. Since it's just a less than, I'm going to finish this graph with an open circle right here. So now let me sketch in what I have. So open circle, and then all of these values that are less than an x value of 1. So that's the first part, is my absolute value graph. Second part is this linear graph. So I start with a y-intercept at -5. So I go down here. And then my slope is 3. So I'm going to go up 3 to the right 1, up 3 and to the right 1. So when I connect the dots, same thing here. It's just going to pick up from an x value of 1 onward. And this one's actually also an open circle because neither one of these have an or equal to. So this point I pick up with an open circle and then use this slope to go here. So I can erase this one. I don't need it because it's not bigger than 1 like this set is supposed to be. So I've got 2 open circles, and so I can use that when I'm setting up my domain because notice there is an x value of 1 that completely gets left off. Like if you're looking to the left, this arrow goes left, this arrow goes right, but these are just complete open circles. If you look at an x coordinate of 1, it never gets hit at all. So the way you write an exclusion like that is to say that x does not equal 1, which basically implies that it will hit every single other value except for that value of 1. And then the range, it goes up, it goes down. Even though there's a little bit of a gap here, that gap in y values is made up over here. So everything gets hit in terms of y, and that would be a range of all reals. All right, more piecewise functions here. Remember, if you have just a number, like the 5 like this, that would be a horizontal line. Okay, so a horizontal line, we start it at a value of 5 like this. And this says for x is less than or equal to 0. So less than or equal to 0 means this value and over to the left. So I'm actually just going to have my horizontal line going to the left. And since this is a less than or equal to, I will have a closed circle here and then going to the left. The more practice you have with these piecewise functions, the less likely you are to have to erase a whole bunch if you can kind of figure out how the domain comes into play. All right, next one. Negative x squared plus 3 only if x is greater than 0. So this one is in vertex form, so I can write down what my vertex would be. So I have the vertex. Remember, nothing inside here means the x coordinate would be 0, and then my y coordinate would be 3, which is that value right there. So 0, 3 would be right here. And then you graph normally by making a table. And again, this is just something that you start to pick up on the more that you use these domains. I normally would center the 0, and then I'd go -1, -2, -3, but that wouldn't fit in with this domain right here. So I'm actually just going to start with the 0 and then only do the right-hand side of the graph, because if I did the left-hand side, I just end up erasing it anyway. So I'm going to plug those values in. Actually, I could probably just do it in my head. I know that I get 3 here. If I plug in 1, -1 squared would be -1, plus 3 would be 2. -2 squared would be -4, plus 3 would be -1, and -3 squared would be -9, plus 3 would be -6. So you can do just that part of it off on the right-hand side. So 0, 3, when I plot this point, it's going to be an open circle, which that doesn't look like a very good open circle, because I've got the pencil in the middle. So let's erase that pencil. There, that looks better. And then 1, 2, 2, -1, and 3, -6. So you've got just this half of a parabola going off on the right-hand side there, because you don't hit any negative x values according to the domain. All right, so domain is all of the x values that get hit. So this arrow goes forever left. This arrow very slowly goes forever right, even though it looks like it's just going down. There's no gap, because this one x value that's missing is made up right here. So my domain would be all reals. And then my range, you look at the y values, you can see here that you skip these y values right here. You have everything up until, but actually not including, the 3, and then it skips right to the 5. So that range would look something like this. Y values such that, and it's 3 and under, so that would be y is less than 3, and then you do your little union symbol to write a separate piece for the range. So then this is just a y value of 5. That's what horizontal lines are. So anything less than 3 or exactly 5. Nothing in between 3 and 5 is hit at all, and nothing bigger than 5 is hit at all. So that's what your range would look like. 23, we've got a relatively complicated one here. You've got 3 different pieces, 1 linear, 1 quadratic, 1 absolute value. So we're going to get to practice everything kind of on one big coordinate system here. So starting with -x minus 9, we're going to do that piece first, and that piece doesn't really require any side work. So -x minus 9, we would start with a y-intercept of -9 down there, and then our slope is -1, so there's no room to go down and to the right, so instead we're just going to go up and to the left, and we'll do that for a little while. Those are easy to do, because you're just going in every corner. And then just up until an x value of -2. So an x value of -2 would be this right here, and according to this, it would be an open circle. So I am going to start with an open circle right here, and then graph everything off to the left. So I'm going to erase these values that I don't need. So that's my first piece. Next piece, this is a quadratic function. So we're going to do our vertex is -1, -5. And I'm going to set up my little table here. However, you want to make sure that you're only using values that could get hit. And it says just values between -2 and +2. So that's all I'm going to put on my table. So values between -2 and +2. All right, so I'm going to start with the vertex, which I know is a -5, and then I can use as much symmetry as I'm able to. All right, so I'm actually going to go to the right because only one of these points is going to be mirrored. So if I plug in 0, I have 0 plus 1 squared minus 5. I'm just plugging into this equation right here. So for that, I get a -4, which I can mirror right here. And then I have to plug these in separately because there's nothing to mirror, because otherwise you'd go back to -3 and -4, and that wouldn't fit inside this domain. So I can plug in 1. 1 plus 1 squared minus 5. That gives me a -1. And then 2. 2 plus 1 squared minus 5. That gives me 4. All right, so I'm going to plot these values. Be careful. So this one, the -2 has a closed endpoint. So at -2, -4, I'm going to put a closed endpoint there. And then I'll plot the rest of these. So -1, -5, 0, -4, 1, -1, and then 2, 4. So 2 is the endpoint, and it's open according to this. So 2, 4 should be an open circle. So just this part of the parabola, make sure you don't extend it any farther to the left or right because it cuts just between these two x values. This left endpoint is included, this right endpoint is not. So this weird chunk of a parabola looks like that. And then we have a piece of an absolute value as well. So let's do some separate work for the absolute value. So that vertex is +3 for x and then 0 for y. So I can... This one, I'd have to still probably start at the value of the vertex. So 3, 0 would be right here. I'm going to do a little bit more work in pencil for this one. And then according to this, my slope is 2. So off to the right, I use that slope, up 2 over 1, up 2 over 1, up 2 over 1. And then off to the left, I do the opposite of that slope. So up 2 to the left one. And I'm not going to go beyond that point because I know this crosses into the quadratics domain. So greater than or equal to 2. So when x equals 2, this would be a closed circle. So it kind of intersects our parabola there. And it looks like this, like a little check mark going off to the right. All right, so that's our piecewise function. A lot of crazy things going on there. All right, so this our domain and our range. Our domain, if you look across, every time there's a gap in the x values, it picks right back up on a different graph. So gap here, but it picks back up. Gap here, but it picks back up. So there are no horizontal gaps at all in my graph. Okay, so for the range, you look for any vertical gaps. So there's a vertical gap right here, but it gets made up in this part of the graph. There's a gap right here, but it gets made up in this part of the graph. And then when you look down below, because the arrows both go up, so when you look down below, there is a minimum value here. So it never goes any lower than -7. So if it never goes any lower than -7, you would write my y values are always above, and it's just a greater than because that's an open circle. All right, so it would look like that. All right, and then topic number 6 here, this is our last topic, kind of a mixed review on all 3 of the types that we've seen so far. So we have a lot of different pieces on end behavior, increasing, decreasing intervals, different things like that. Okay, so we're going to be practicing just basically everything that we've done so far in this chapter. So this is absolute value. So when you write each one of these down, you're going to write what the parent function is as well. So this parent function was an absolute value graph. And they're easy to spot because if it literally has the absolute value symbol, that makes it an absolute value graph. So the thing you want to do is plot the way that we've learned how to plot it first, and then use the graph in front of you to write down all this stuff. So for absolute value, we plotted by using the vertex and the slope. So the vertex would be +3, +4. So we start there, like that. And the slope is the number in front of the absolute value, so it's a 1. So off to the right, I use a slope of 1, and then off to the left, I mirror it. Okay, so that is my graph. Domain, remember, for all absolute value graphs is all reals. So the only time the domain isn't all reals in this chapter is if you're dealing with a piecewise function that has horizontal gaps in it. Otherwise, if it's just linear or absolute value or quadratic and it's not part of a piecewise, the domain will always be all reals. Okay, and then range for absolute value depends on where the y value for the vertex is. So this y value is 4, and then it goes up from there. So we would say y is greater than or equal to that value of 4. All right, number of roots would be x-intercepts, and there aren't any. It doesn't cross through that x-intercept at all. As x approaches infinity, so that means as your graph moves to the right, your arrow goes up. So this would be infinity. This one means as the graph goes to the left, so as the graph goes to the left, again, the arrow goes up. And then increasing and decreasing. So this first part of the graph is decreasing. It decreases all the way up until this x value of 3. So it decreases from negative infinity until 3. And then for the rest of the graph after that, it increases. So it increases from 3 onward. Okay, so now we've got a few more, 4 more of these graphs on the next page. Just mixed practice, like the topic says. So this one is a linear function, and really these ones are like process of elimination. If it doesn't have absolute value and it doesn't have a squared in there anywhere, then it must be a linear function. All right, so plot, we start with our y-intercept, which is at 2, and then our slope is negative 6 over 5. So we go down 6 and to the right 5, and we do run out of room to go up and to the left, but that's okay because 2 points is plenty. Actually, we don't run out of room. We can go right there. So connect the dots. This is our linear function right here. And then let's fill in all of this information. Linear functions for domain and range is easy. It is all reals for both. So no matter what linear equation, as long as it's not part of a piecewise, the domain and range is all reals because it goes left and right forever. It goes up and down forever. Number of roots is crossing through the x-axis. That happens once right there. So we have 1 root. And then our end behavior takes a look at those arrows at the end of the graph. So as my x values go to the right, that's this arrow right here, my graph goes down. So that would be negative infinity. As my x values go to the left, my arrow goes up. So that would be positive infinity. Increasing interval, there actually isn't one at all. Linear functions either completely increase or completely decrease, and this is completely decreasing. So there is no increasing interval, and decreasing is just everything. So from negative infinity to positive infinity, every single value it's decreasing. All right, 26, we've got a quadratic. When you see the squared right there, you know it's going to be quadratic. So we start by finding the vertex. The vertex, we use x equals negative b over 2a. So negative 8 over negative 2 is a positive 4. So as soon as you know that value of the vertex, you can use that to set up a table. So our vertex goes in the middle, and then we go down and up from there. All right, so that, we can plug the first 4 into the calculator and then use symmetry. So 1, we have negative 1 squared plus 8 times 1 minus 14. None of them are negative, so I don't have to be super cautious with parentheses. So this is a negative 7, and so is this. 2, negative 2 squared plus 8 times 2 minus 14. That is negative 2, and so is this. 3, negative 3 squared plus 8 times negative 3. Sorry, not negative 3. The negative is from the formula. Minus 14 is 1, and so is this. And finally, our vertex, negative 4 squared plus 8 times 4 minus 14. That is 2. So we use that table to plot all the points. So we start with 1, negative 7, 2, negative 2, 3, 1, 4, 2, and then there goes our symmetry. Okay, so connect the dots. Looks like that. And then for our domain, if it's just a quadratic, our domain is all reals every time. And then for quadratics, our range depends on where the y value of the vertex is. So the y value of the vertex is 2, and then it goes down from there. So if you go down from a value of 2, your range would be y is less than or equal to 2. Number of roots is how many times it crosses through the x-axis. We've got 1 here and a second 1 here, so that would be 2. The end behavior is where arrows are going. So as our x values go off to the right, that's this arrow. That arrow is going down, so that's a negative infinity. As my x values go to the left, so that is this arrow, that arrow is going down as well. So these should always match with quadratic and with absolute value. So let's look at increasing, decreasing. It increases up until it hits its vertex. So starting at negative infinity up until this vertex, and that x value is 4. And then once it hits its vertex, it decreases for the rest of its range. So it decreases starting at 4 and then going on from there. All right, 2 more. 27 is a linear function, and again, that's just the absence of the absolute value bars or something that's squared. If it doesn't have either one of those, it must be linear. We start with the y-intercept, which would be at -4, and then this one has a slope of 1. So we can just do a couple up 1, over 1s, just to get a good idea of the graph before we connect the dots. Okay, so that's our linear function. Again, linear functions, the domain and range is always all reals. It goes all the way to the left and to the right. And for the range, it goes all the way up and all the way down. So that would be all reals again. Number of roots is 1. It crosses through the x-axis in just one spot. That's true for all linear functions. The number of roots is always 1. End behavior, these ones should be opposite. Because notice like quadratic, the arrows go in the same direction. With linear, they go in the opposite direction. So as my x values go to the right, that's this arrow, my function goes up. So positive infinity. As my x values go to the left, that's this arrow, my function goes down. So that is a negative infinity. So again, with the linear, these should be opposite. And with lines, just like we talked about with 25, they're either all increasing or all decreasing. This one is all increasing. So we say it increases forever, and this is the set that we would write to say that it increases forever. And then it doesn't decrease at all. So we would just write that for the decreasing interval. Or you could do a little slash, something, or none, whatever you want to do. All right, last one here is number 28. We see a squared right there, so that makes it a quadratic. And then we can set up the vertex and our little table. So the vertex is -1 for the x-coordinate and 0 since there's nothing added or subtracted there. And one last table we will make for this one. So the -1 goes in the middle, and we go down 3 values and up 3 values, like that. All right, so we know this value is 0. We can plug in these 3 values and then mirror them. So -1/2, I'm going to use -0.5 and then times -4 plus 1 squared. So this is -4.5, which we can mirror. Next value is a -3, so -0.5 out front. Oops. And -3 plus 1 squared. So that is a -2, which gets mirrored here. And last one is the -2, or you could plug in the 0 and mirror it here. I just do the left because those are the first ones that are listed. So the -2, we have a -0.5 out front, -2 plus 1 squared. And that would be -0.5, which means so is this one. All right, 7 values to plot. So -4 goes down to -4.5. -3 is at -2. -2 is at -0.5, so just halfway down there. -1 is at 0, and then we show our symmetry like that. Okay, so that would be our parabola. And finally, we can answer these questions over here. So a standalone quadratic always has a domain of all reals. The range depends on where the vertex is, so the highest possible y value is 0, and then it goes down from there. So my y values are those that are less than or equal to 0. Number of roots, it actually just touches the x-axis 1 time, so that would be 1 root. And our end behavior is these end arrows that we look at. So as the graph goes to the right, that's this arrow, my function values go down, so -infinity. And as my graph goes to the left, that's this arrow, my function values go down again. Remember with 26, I mentioned quadratics, these two things should always match. All right, last thing, increasing, decreasing. So my graph increases up until this point, which is an x value of -1. So everywhere to the left, and then it stops increasing at -1. And then from the vertex over to the right, it just decreases. So starting at -1, it then decreases for the rest of our numbers. So it would look like that.